if we look experimentally, what we see, it's actually a little bit different. It's negative 411 kilojoules per mole. So in terms of this class, this is the method that we're going to use, and we're going to say this gets us close enough such that we can make comparisons and have meaningful conversations about different types of ionic bonds and the attractions between them. But let's think about where this discrepancy comes from. And before I do that, I want to point out one term we use a lot is change in energy for a reaction where, for example, you break a bond. Remember that the negative of the change in energy is what's called delta E sub D. We first saw this when we first introduced the idea of covalent bonds. Do you remember what this term here means, delta E sub D? A little bit and some no's, which this was pre-exam. I understand you still need to review those notes. It's dissociation energy. So you get a negative energy out by breaking the bond. The dissociation energy means how much energy that bond is worth in terms of strength. So it's the opposite of the energy you get out of breaking the bond. Or excuse me, the energy that you get out of forming the bond. It's the amount of energy you need to put in to break the bond is dissociation energy. It takes this much energy to dissociate your bond, excuse me. All right, so let's take a look here at our predictions. So I just put them both ways so we don't get confused. The dissociation energy is 444. The change in energy for forming the bond is negative 444. We made the following approximations which explain why, in fact, we got a different experimental energy if we look at that. The first thing is that we ignored any repulsive interactions. If you think about salt, it's not just two single atoms that you are talking about. It's actually in a whole network or whole lattice of other molecules. So you actually have some other chlorines around that are going to be having repulsive interactions with our chlorine that we're talking about. We're going to ignore those, make the approximation that those don't matter at this point in these calculations. And the result for that is that we end up with a larger dissociation energy than the experimental value. That's because the bond is going to be a little bit more broken than it was in our calculation because we do have these repulsive interactions. The other thing that we did is that we treated both sodium and the chlorine as point charges. And this is what actually allowed us to make this calculation and calculate the Coulomb potential so easily. We just treated them as if they're point charges. We're ignoring quantum mechanics in this. This is sort of the class where we ignore quantum mechanics. We ignored it for Lewis structures. We're ignoring it here. We will be back to paying a lot of attention to quantum mechanics in lecture 14 when we talk about MO theory. But for now, these are approximations. These are models where we don't take it into consideration. And I think you'll agree that we come reasonably close such that we'll be able to make comparisons between different kinds of ionic bonds.